me share my screen. You guys see my screen, right?
Yeah.
Okay, so number 3 for this week's contest was called Shortest Paths. And basically what it was you have n different towns or nodes numbered 1 to n, and n roads or edges between them. I wanted to determine the length for the shortest path from town 1 to every other town. This is basically just asking you to implement Dijkstra's algorithm. So I'm just gonna explain Dijkstra first and then go back and code it up here and according to the problem. Okay, so Dijkstra, for Dijkstra, you are given like a starting node and you want to find the Dijkstra's algorithm can find all of the shortest paths, all the shortest path links to all of the other nodes. And time complexity of Dijkstra is O of n plus m log n, m log m, where m is number of edges, n is number of nodes. And so obviously for this problem that we were looking at, this is fast enough. And so I'm just going to explain the algorithm now. So Dijkstra's algorithm finds the shortest path from the starting node to all nodes of the graph. And the algorithm requires that there are no negative weight edges in the graph. Weight edges are basically like, okay, suppose you have a bunch of nodes in a graph, and connections between them. These connections are called edges, and the weight edges, the edge weights are, each of these are assigned a number, and these are called edge weights. And in this scenario, the edge weights represent the cost of traveling, using the connection between the two nodes. And each of the nodes this time, like they represent a town. Okay. Now, Dijkstra's algorithm starts with an initial node. Let's just designate this node as it, and suppose it's numbered node 0. This is number node 1, node 2, node 3. Okay, I'm gonna draw some more nodes just to make the graph more complicated. 1, 0, 1, 2, 3, 4, 5, and 6. And then basically it maintains distances to all of the nodes and then reduces them during the search. So initially all of the distances are set to infinity except for the initial starting node that is designated as the starting node, which we'll say is node 0 in this case, and was the case in the problem. So the distance would be 0. All the other ones would be infinity. And then it basically you keep in a priority queue, which is a data structure that maintains all elements, with the top element being the smallest distance, and you can remove that element in log n, and basically you keep in that all the distances, and during each step of the algorithm you process one node in the graph, and you always process the node that is the closest to your starting node and hasn't been processed yet. So for example, I'm just gonna run the algorithm on this graph. The first step of the algorithm starts off with this node 0, and basically like you see that the distance to node 0 is 0, and then it looks at all the possible edges, and looks at all the possible neighbors, and it reduces the edges. So then there's one edge over here, so 0 plus 1, that means the distance to 1 is actually 1, and it'll reduce this infinity, to just 1. And then it's done processing this node, so then it moves on to the next node in the priority queue, which then you find out is 1, because this is now the next closest node, and it checks all of its edges, and then like 1 plus 2, that means the distance from 1 plus the edge length 2 equals 3, which means this is in reality a distance of 3, and this has, let's say, edge weight 1, and then 1 plus 1, 2. This in reality has distance 2. This probably has like, let's say 10. This has distance 11. And then whenever like you update a node, you reduce a distance in the graph, you add it to the priority queue, so that basically whenever when you do this, Dijkstra essentially visits each of the nodes in the graph in the order of the distance, because it always visits the node that is the closest to the possible graph. And once you process a node, so like for instance, once we process node 1 right here, you can't possibly reduce it any further, because whatever like edges you travel, all of the like you can't possibly reduce the distance from to node 1 with using any other node, because in order for it to have been processed, it must have been in the priority queue. It must have been in the head of the priority queue, and that means it would have been the thing with the lowest priority, meaning it had the least distance at some point when it was in the priority queue, and then it got removed. So that meant like that means that all the other nodes have distance greater, and whenever you all the other nodes have distance greater, you can't possibly reduce it to a distance less than the original distance. Yeah, I think it'll be easier if I just keep on working through this example. Okay, and then the next closest node is node 4, but it looks at this edge, and then 2 plus 1 equals 3, but node 1 is already at a distance 1, so this isn't optimal to take. So it skips that, and then it looks at this node 2, it's at distance 3. 3 plus 2 equals 5, but node 1 is already at a distance of like it's at a distance of 1, so it's not beneficial to take. And now we look at node 3, and it's 3 plus 3 equals 6, and that is less than infinity, so obviously we take that for 6. And then we're done processing 2, and then now we process 3, since it's the next closest node, because at this point, the priority queue only contains nodes 3 and 5 with distances 6 and 11. And 6, it's not beneficial to use this edge, but it is beneficial to use this edge with, suppose, 1. So 6 plus 1 equals 7. So you reduce this, and yeah, this is 7. And then you go, the next node you process is 5. And then 5, let's suppose this is 1. And then 7 plus 1 equals 8. And then in the end, all the different distance values you have are the shortest possible lengths to each of the nodes. Let's say this. Okay. Yeah. Okay. For negative edges, the reason that you can't have negative edges is that the algorithm may give incorrect results, I'll give an example of where the algorithm gives incorrect results. So suppose we're looking at this graph: 1, 2, 3, 4. Let's say 2, 3, 6, and 5. What this does is these are the nodes, and these are the edges, and it visits the closest node, which is 1 at the beginning because it's 0, and all the other ones are infinity. It does this. It analyzes all the different possible paths, and it finds out that this one should be 2, this one should be 6, and then it visits the next closest node, which is 2, and then 2 plus 3, 5. So that means this is now 5, and it visits the next closest node, which is actually which it recognizes as node 4, and then since its distance is 5, okay, this weight was supposed to be -5. This is the negative edge, right? Then it looks at this edge, -5, and it reduces this down to 0. And at this point, since the algorithm already processed this node, processed this node, processed this node, it will process this node again, and then it'll say this 0 plus -5 is -5. So it'll say the distance is -5, and then it'll say this is process 2. But this is clearly not like the case, because you can always like, it's supposed to be -1, because this is actually the shortest path. 6 minus 5 equals I mean, it's supposed to be 1. 6 minus 5 equals 1. But it gave the wrong answer. So yeah. So I think that's it for the Dijkstra's algorithm. I'm gonna switch to doing the problem now. 1 second. Okay, so basically, I'm gonna implement it. We need to first include a class storing all the different nodes. Okay, and then it will store the destination in the distance. This is the constructor. And then we're gonna do a comparator. This comparator is to be used in the priority queue. And we want the priority queue to sort by the nearest distance. So this is what we're gonna do. Oh, this. Okay. Now I'm gonna read in the input really quickly. Oh, oops. be bug free now. Okay. We're reading in. And we're going to be keeping this inside of a adjacency list. So we're just going to do that. Oh. We need to initialize all the array lists. And then we're reading all the edges. All right. You notice that in the problem, they give you all the edges in the form where all the different like nodes are numbered from 1 to n. Just for convenience, I'm gonna subtract 1 from all of these. So I made it 0 index instead of 1 index. So these are the two nodes. This is the edge length. And since this is a directed graph, you only add it once. Oh, I wanted to mention that Dijkstra works for both directed and non-directed. And then now we create a priority queue. Okay, and then to do Dijkstra's, we need to keep an array of Booleans that mark whether each node is visited. And then we need to have a long array to store all the different distances. And then we'll initialize all of these to infinity. In this case, it would just be long dot value. And then I set the initial distance equal to 0. And then you also have to add the initial edge. The initial like distance from 0 to 0, from node 0 to node 0, which is 0. And then you have a while loop. And while the priority queue stuff still has nodes, you process each node. So you pull up the top, and this is the node with the lowest priority so far, which means it's the closest to the initial node, which in this case is 0. And if it's already visited, then you don't need to visit. Otherwise, you mark it as visited. And then you go through all the different edges. And check if it's beneficial to use the edge. If it is, you update the distance. And then you add a new node, okay, these aren't really edges. I just used edge for convenience, but like, I just used the edge class for convenience because I already implemented it. These are just like, these just store the distances to each of the different nodes. This is the next destination, and this is the distance. And then now, you just print out all the values. And that's it. Oh, I don't think I threw IO exception. Okay, yeah. Oops. Oh yeah, I did throw IO exceptions. Something's just wrong with my code. All right. Let's see. That's fine.
I think it's because your edge class is not a static class.
Static class. Oh, okay. Yeah. Bruh. Possible loss information from.
You didn't print out anything, right?
Wait, I think
What?
it's because dest is a long. Wait, can you see what data type dest is?
Yeah, it's a long.
Yes. Wait, no, dest is a. Oh yeah, okay.
Distance is a long. And then.
Do you assign
which line is this? 51. Oh yeah, this should work now because I changed the constructor to taking it in a long. And oh, okay, I printed it wrong apparently. 052. There we go. All right, finally. Okay, and that was the solution. After this meeting, I'm gonna this code will be uploaded to the public drive, and you can use this as like a template for future like implementations of Dijkstra, because this is like basically the standard implementation of Dijkstra that you can just copy and paste, but not for useCode because useCode doesn't allow templated code. All right, does anyone have any questions? Okay.